The mole is a number of particles that brings us from the atomic world to the macroscopic world, the stuff that we can see and measure. Specifically, if we have 6.02 times 10 to the 23rd particles of something, that could be atoms or molecules or pieces of ionic compounds we call formula units, when we have that many particles of something, we get the same value of mass, but instead of it being in atomic mass units, it's in grams. So on the periodic table, we're going to stop talking about the average atomic mass as AMU, and instead we're going to refer to it as the molar mass. How many grams of that element we have in 1 mole of that element? If we're working with just one element specifically, that's all we kind of need to go between grams and moles of something. And if we want to figure out particles, moles is the place to be. So moles is kind of like the in-between between grams and particles. Okay. If we have more than just one element, like a compound or a diatomic substance, then we just have to add up the mass of a couple atoms or however many is in that chemical formula, and we get the molar mass of that substance rather than just that one single atom, that one single element. So we're going to go through some examples of this. There's a couple extra notes up here at the top that can be helpful just to kind of keep track of how we're going to be converting between these. In the end, the math should be very familiar to us because it's no different than any other kind of unit conversion. We're just going to be using conversion factors that we're not as familiar with. So let's check out this first one. How many moles of selenium are in 380.0 grams of selenium? Well, okay, so I'm starting with a unit of grams. I'm going to be getting to a unit of moles. Okay, so I'm going to need to do a conversion. And even if I don't know how to do that conversion yet, I know how to start it. I have data that I can convert, so let's start with that out front here. 380.0 G for grams, SE for selenium. Okay, now I want to get rid of my grams unit. To get rid of it, I'm going to have to divide it by something else with the grams unit. In order to get the moles unit, I have to multiply by something with the moles unit. So instead of having to do two separate steps of divide by this, multiply by this, we do a fraction bar. All right, where we have grams on the bottom here. So that way that'll divide and cancel out, and moles will be on the top. Okay, just as a reminder, a refresher, whatever's on the top of our fraction bar, we multiply by. Whatever's on the bottom, we divide by. Okay, so if I can figure out this conversion factor, I can convert from grams to moles, but I need to find an equivalent number of grams and moles specifically for selenium. In other words, how many grams of selenium are in a mole of selenium, or vice versa? Well, that's what the molar mass is all about. If I go look at a periodic table, that should tell me how many grams of selenium are in 1 mole of selenium. So if you don't have a periodic table and a calculator ready, you're going to need them both today. So let me go find my periodic table. So I'm ready to. All right, selenium has a molar mass of 78.97 down at the bottom of its little element block. That means it has a mass of 78.97 grams for every 1 mole of selenium that there is, for every 6.02 times 10 to the 23rd particles. Okay, so we got that taken care of. Our units here, again, should cancel. Grams of selenium should go away. I should be left with moles of selenium. So all I have to do is work out the math. I take 380.0 times 1 divided by 78.97. Get my calculator out here. Where I put it. There it is. All right, plug this in. All right, and I get about 4.812-ish And my new unit is moles of selenium. All right, and that should be my answer. Okay, after all, if I had 78.97 grams of selenium, that would be 1 mole. I definitely have more than 78.97 grams, so I'm going to have more than 1 mole, which is what I got over here, so it's making sense. As far as your answer goes, usually 2 or 3 decimal places is pretty good. There are rules out there for how exactly you chop off your answer and round off, but we're going to stick to just, 2 or 3 decimal places is good for now. We don't need to add another step to this. Okay, let's look at another problem. How many molecules of carbon dioxide are in 3.50 moles of carbon dioxide? Okay, well, again, I'm starting with 3.50 moles, and I want to get molecules instead. That's just another word for particles. Particles. A molecule is just a collection of atoms that are grouped together, and they stick together, and they're a kind of particle. So I'm going to have to start with this 3.50 moles. 3.50 moles. Let's see, carbon dioxide is CO2. Moles of CO2. Set up my fraction bar. Okay. So I need to get rid of my moles unit this time, which means my moles unit has to go in bottom. Whatever I'm canceling and dividing by has to go in bottom here. They got to be on opposite sides. Okay. So what I'm trying to get to is going to be what I multiply by, which would be molecules. Or in this case, I'm going to call it particles, so it's a little more general. Particles of CO2. I'm going to need this fraction bar to be longer. There we go. So again, I have another conversion factor where I need to figure out what's going to be the numbers in here. What am I actually multiplying and dividing by to get my units to cancel correctly? Okay, well, the mole is defined by how many particles there are, or how many things of anything there are. It's just like a dozen. It's just a number. So as a reminder, a mole specifically is 6.02 times 10 to the 23rd particles of something. It could be carbon, it could be selenium, or it could be molecules of carbon dioxide. So if I had 1 mole of CO2, that would be 6.02 times 10 to the 23rd particles of CO2. Okay, and this might be a little bit hard to put into your calculator depending on what you're using, which is why I have a calculator that writes it out exactly as I would put it in the math. I like scientific calculators that have space where it saves where you write your stuff. You can go back to it, and it will type it again like you would write it out in math. So 3.5 times 6.02 times 10 to the 23rd divided by 1. All right, and if you're not sure how to get your calculator to do this, as long as it's got some scientific function, it's got some of the fancy things like exponents and stuff, it should be possible. It just might be harder than it usually be. So if you're stuck on that, let me know and I can help you. I can show you how to use your calculator to get this stuff to work. Okay, usually also stuff on the internet works pretty well. If you have like a computer calculator or an online calculator, something like that, that usually works pretty well too. Okay, 3.50 times 6.02 times 10 to the 23rd divided by 1 should give us moles canceling out, particles unit left over, and our answer is something around 2.107 times 10 to the 24th particles, or you could say molecules, particles or molecules of CO2. And that's our answer. Okay, again, we had more than 1 mole of CO2, so we should also have more than 6.02 times 10 to the 23rd particles, which is what we have. So, nice. Looks good, looks good. Let's keep on moving. Let's check another problem. How many molecules of dichlorine are there in 2.00 grams of dichlorine? Okay, well, this time we're trying to go from grams to molecules, okay, which is particles again. So this is Let's do red this time. Let's switch back. So this is particles. And we just show that we can get to particles from moles. We can get to moles from grams. So we're going to kind of put those things together. We're going to be going from grams to moles, and then moles to particles, like molecules. So we're going to be kind of stringing these two together. All right, so let's do this. Let's give myself some room here because this is going to be a longer one. 2.00 grams. Let's see. Dichlorine would be Cl2. 2.00 grams of Cl2 times. Okay, I'm trying to get rid of grams of chlorine, so that has to go on the bottom. My old unit always goes on the bottom. All right, my new unit is going to be moles. I can go from grams to moles, and then moles to particles. So we're going to make kind of a pit stop at moles first. Moles Cl2. Okay, so in 1 mole of Cl2, how many grams of Cl2 do I have? Well, this isn't just one atom of Cl, so it won't be as easy as just looking up Cl on the periodic table, but we will need to do that. Okay, since there are 2 atoms of Cl in each of these molecules, each of these particles, I'll need to add up the mass of 2 Cl's. Okay, whatever's in the formula, I got to add up. So to get this molar mass here, I have to add up 2 atoms of Cl, or we could multiply 2 times however much your molar mass is for that element. So chlorine's molar mass is 35.45. If you check that on the periodic table, grams per mole. If I take that times 2, I should get 70.90 grams of chlorine or dichlorine for every mole of dichlorine. Okay, so that should help me cancel out my grams units. Okay, if I take 2.00 times 1 divided by 70.90, I'll change my answer into moles of Cl2. But again, that's not really where we're ending. So we could say, okay, I'm going to stop here and get my answer for my moles and calculate that. But if we know that's not the answer that we want, we can also just string on another conversion. Now the unit we're trying to get rid of is this moles of Cl2. So I'm going to put moles of Cl2 on the bottom of the next fraction bar. Okay, rather than stopping and having to make another, calculation in your calculator and all that stuff, we're just going to keep going. Okay, I know I'm not at the unit I want yet, so now that's going to be the next thing to get destroyed by putting it on the bottom of the next fraction bar. So moles of Cl2 is going on the bottom of the next fraction bar. And then on top, I'm trying to find particles of Cl2. Particles of Cl2. Okay, so I've got another conversion factor. Ooh, that's not a very good rectangle. Let me see if I can fix that a little bit for my sake. That's a little better. Okay, so I need a relationship between particles and moles, and hey, that's what that big nasty number, that 6.02 times 10 to the 23rd is for. In 1 mole of whatever, so it could be single atoms of chlorine or it could be dichlorine molecules, I have 6.02 times 10 to the 23rd particles of that stuff. I'll just squeeze this in, 23rd. There we go. All right. Now, my units should be able to cancel from moles and go to particles instead. So I should be able to convert from grams to moles and then moles to particles. I can stop at particles because that's the unit that I want. All right, so now I just have to plug this in. So I can take 2.00 times 1 divided by 70.90 times 6.02 times 10 to the 23rd divided by 1, and I should get my answer. Now, it's good to know that multiplying by 1, dividing by 1 aren't actually going to change your answer. It should just give you the same thing. But it can sometimes be useful, especially if you're like me and you lose track of stuff in your calculator. Sometimes if I try and start to skip ones, I start to multiply things and divide things, and I forget something. I'm like, oh yeah, I already did this first fraction bar because I multiplied this first, and then I don't actually divide by this, and then my answer comes out wrong. So I sometimes like to just do all of it and say times 1 divided by this, times this divided by 1, and it takes a little bit longer, but I make sure I hit everything. But it's totally up to you. If you can just say, I'm going to take 2.00 divided by 70.90 times 6.02 times 10 to the 23rd, that is totally fine. Won't change your answer as long as you make sure you hit everything that's not a 1. So let's plug this in. 2.00 divided by 70.90 times 6.02 times 10 to the 23rd gets us 1.698-ish times 10 to the 22 particles or molecules of Cl2. All right. Okay. And that answer is looking pretty good. If I had a whole mole of Cl2 particles, I'd have 6.02 times 10 to the 23rd particles. I don't. I have way less than that. I have, like 2 grams instead of like 70. So this is going to be less than that 6.02 times 10 to the 23rd big nasty number. So that checks out. It's not a guarantee that my answer is right, but shows that I'm on the right path. Okay. Now, when you start doing longer conversions like this, sometimes it can get a little confusing of what goes on top and what goes on bottom. But usually it's not the units that get us kind of tripped up, because I usually hammer it in enough that it's like old unit goes on bottom every time, old unit on bottom, old unit goes on bottom. But then we kind of get switched up on where we put the numbers, especially when we get into examples like the next one where we don't do it in the same order that we might do in other problems. So in the next one, we're going to be going from particles to moles instead of moles to particles. So it's like, well, I put the particles, the big nasty number, on top last time. Now it goes on bottom, and it trips people up. So if you're ever kind of uncertain about what number goes in what spot for your conversion factor, I have this advice for you. I'm going to put it down here so I don't end up scrolling past it. B1 with moles. Okay, so if you are not sure what goes in your conversion factor and you don't even know where to start, take a deep breath and B1 with moles, which means put a 1 in the mole spot. Okay, then you just got to figure out what 1 mole of that other stuff would be. If you have 1 mole of something, how many grams do you have? Look at the periodic table. If you have 1 mole of particles, how many particles is that? That's that big nasty number, that 6.02 times 10 to the 23rd. So it might help to be able to fill in a spot so you know where one of those things goes, and specifically the 1 goes, and then you can find the other piece of that. Okay, let's test it out. How many moles of calcium sulfate are there in 8.99 times 10 to the 24th formula units of calcium sulfate? Okay, well, formula units is just a number of particles for an ionic compound. We don't really call them molecules because usually that's kind of reserved for covalent bonding. For ionic compounds that repeatedly stack up, cation, anion to make a huge network of a whole bunch of charged atoms, we don't really have a single group of atoms that make a molecule. It just kind of continues as for as many ions as you can clump together. So instead, we call them formula units. It's kind of the lowest ratio of that ionic compound. In this case, our compound is calcium sulfate. So let's start out our problem with this 8.99 times 10 to the 24th. Try and convert it into moles of calcium sulfate. So let's see here. So 8.99 times 10 to the 24th. Okay, this is particles of calcium sulfate. That's CaSO4. Okay, if you're not sure how I got that, calcium as an ion has a +2 charge. Sulfate as an ion is a polyatomic ion. It's sulfur lodged in with a whole bunch of O's, specifically a sulfur with 4 O's, and altogether has a -2 charge. If I put together one of these calcium ions and one of these sulfate ions, the +2 and the -2 cancel. So I don't need more of one or the other. One of each is just fine. So my formula is just CaSO4, like I've got here. Okay. Let's do our conversion. I think I'm actually going to need to move this a little bit. So I've got some more room here. That's a little better. Okay. In this case, I'm trying to get rid of particles. So I want to put the particles unit on bottom. Particles, CaSO4. Yeah, I'm really going to run out of room here. Wow. On top, I'm going to have moles. I'm looking for moles, CaSO4. Okay. Well, now particles are in a different spot. It's making me kind of uncomfortable. So what do? I take a deep breath, and I'm going to be 1 with moles, which means I put a 1 right there with my moles. Okay, so I've already got half the conversion factor done. Now to figure out the rest of it, I just have to ask myself, how many particles are there in 1 mole of whatever? Well, that's got to be that big nasty number, that's 6.02 times 10 to the 23rd particles. Okay, from there, we're just going to multiply by the top, divide by the bottom. Now, there's something you have to be careful of, especially with calculators like the one I have that are scientific. Sometimes your calculator will try and be smarter than you are. And it's not really, it's just trying to follow the rules. Those rules specifically are the order of operations. If I type this in as is, 8.99 times 10 to the 24th times 1, divided by 6.02 times 10 to the 23rd, what your calculator reads is, oh, I get it. You want me to take 8.99 times 10 to the 24th times 1 divided by 6.02 and then multiply by 10 to the 23rd. Which is not what we want. We want to divide by this whole thing. So that's not going to work out too well for us if we just type it in like that. So to get your calculator to recognize that this is all one thing, make sure you put parentheses around it in your calculator. Okay, you want to divide by parentheses 6.02 times 10 to the 23rd, end parentheses. Okay, so make sure you put parentheses around this. If you get an answer that has like, write it down here, answer with something like 10 to the 47th or 48th or something like that, something went wrong. You should probably try it again. Probably means that you ended up multiplying the 10 to the 24th times the 10 to the 23rd. Maybe not on purpose, but your calculator tried to do it for you. So make sure you have parentheses around this whole thing. So let's try and throw this into our calculator. 8.99 times 10 to the 24th. 8.99 times 10 to the 24th times 1, which doesn't do anything, divided by parentheses 6.02 times 10 to the 23rd. Close my parentheses, and now I can put in my stuff in my calculator. I get 14.93-ish. 14.93-ish moles of calcium sulfate, CaSO4. And that's my answer. Okay, I have more than 6.02 times 10 to the 23rd particles of something, which means I've got more than a mole of it. Specifically, I have 14.93 moles of calcium sulfate. So nice, that's my answer. Okay, so be aware of that. If particles is on bottom of your fraction bar, put the whole thing in parentheses. Okay, and it doesn't hurt to put it in parentheses otherwise too. It's not going to make anything go wrong. It can only help you make it go right. So put the 6.02 times 10 to the 23rd in parentheses, especially if you're dividing it. All right, let's look at one more. How many grams of magnesium nitrate are there in 4.85 times 10 to the 23rd formula units of magnesium nitrate? Okay, well, 4.85 times 10 to the 23rd 4 million units. That's a number of particles. And it's less than our 6.02 times 10 to the 23rd. So this is not going to be a whole mole of something. It's not going to be a whole mole of whatever this chemical is, which is magnesium nitrate. Okay, so before we go and write out the whole thing, let's do this. We're going to do our 4.85 times 10 to the 23rd. I'm going to say part instead of particles so I can fit this in the whole screen. It's particles of, well, magnesium nitrate. Let's figure out what this magnesium nitrate is. And I promise it's going to be important later. So it's not just me trying to throw in extra practice on your conversion problems. So let's see. Magnesium is Mg. On the periodic table, we can see that it should have a positive 2 charge as an ion. Nitrate is a polyatomic ion, like sulfate. How that's sulfur with a bunch of oxygens on it. Nitrate is nitrogen with a bunch of oxygens on it. And specifically, 3 oxygens can cram into that 1 nitrogen. Nitrate has a negative charge, which means that one of these nitrate polyatomic ions is not going to be enough to cancel the positive 2 charge of this. So to fix that, I'm going to wrap this whole thing up in parentheses. Put a 2 down here to say that there are 2 of those whole nitrate polyatomic ions. There's 2 NO3s. That means I should have 2 negative charges to be able to cancel with my positive 2 charge, which is a good sign of a happy ionic compound. So my formula of magnesium nitrate is Mg, and then parentheses NO3, and that whole thing is there twice. It's MgNO3 too. Okay. So let's convert. I'm going to draw a multiplication, get a fraction bar going. I want to get rid of particles, so particles is going to go on bottom. I'm going to abbreviate with part. MgNO3 2. And then I want moles on top. Moles is my kind of in between particles and grams. So let's make a pit stop at moles first. Moles of MgNO3 2. All right. So what I'm going to do, I'm going to be 1 with moles. I'm going to put a 1 with moles up there. So I go to 1 on top. How many particles are in 1 mole of something? That is 6.02 times 10 to the 23rd. There we go. I've got that fraction bar done. But again, this is not where I'm ending. So rather than calling this a day and calculating out what the answer is here, I'm just going to keep going. I need another fraction bar where I'm going to change from moles into grams. And I'll probably just have to squeeze my answer in down here somewhere because I've run out of room again. Okay, so now that I've gotten rid of particles, my next unit to get rid of is moles. So I'm going to put moles of Mg, this is going to be tight, NO3 2. Oh, that's not very good, but that's okay. Moles MgNO3 2 down on the bottom. I should have grams of MgNO3 2 on the top. Okay, so what do? I gotta be 1 with moles. I'm gonna put a 1 down there with the mole. So I'm gonna be 1 with moles. And I've just gotta ask myself, how many grams of MgNO3 2 are there in 1 mole of MgNO3 2? Well, if I just had Mg, I would just go look up Mg's molar mass on the periodic table down at the bottom of its block, and it'd be like 24.31. But I also have some other stuff. I have 2 N's and 6 O's in here. So to get the whole molar mass of this, I need to add up an Mg, 2 N's, and 6 O's. So let's put that together. Let's do green. So I need 1 times the molar mass of Mg plus 2 times the molar mass of nitrogen plus 6 times the molar mass of oxygen. Okay, and don't forget about this 2 here. That means there's 2 times as many N's as O's inside of that parentheses. Magnesium's molar mass is 24.31 on the periodic table, 24.31. Nitrogen is 14.01. 14.01. Oxygen is 16.00. 16.00. All right, so I'm going to take all that and crunch it together. 24.31 plus 2 times the 14.01 plus 6 times 16. All right, and I get a molar mass of 148.33 grams for every mole of magnesium nitrate, MgNO3 Okay, so that's going to be the mass I put up here. In 1 mole of MgNO3 I should have 148.33 grams of it. Okay, my moles units should cancel. I'm going to be left with grams. Okay, so now all I have to do is plug stuff into my calculator. Again, I've got to be careful. I have to make sure that, let's do a different color this time. Let's do this kind of greenish blue. I've got to make sure this 6.02 times 10 to the 23rd is going to be in parentheses. So we're kind of putting it all together. That whole 6.02 thing has to be in parentheses. So I divide the whole thing. So let's do this. 4.85 times 10 to the 23rd times 1 divided by parentheses 6.02 times 10 to the 23rd. Close my parentheses. Times 148.33 divided by 1. What I get, let me just kind of put this down here, equals, I get 119.5-ish grams of MgNO3 And that is my answer. Okay, now I want to mention real quick, there isn't anything technically wrong with stopping after this conversion, getting an answer, and then doing another fraction bar to convert, but it will save you a lot of time to be able to just string these together and punch it all into your calculator at once, especially because we might not stop at conversion factors that take 2 fraction bars. We might go on to do one that take 3 or maybe even 4. So again, it will start to save you a lot of time if you practice it now and get used to doing multiple conversions kind of in a row rather than stopping every time you do a conversion. Okay. Something else I want to mention. We did really need this formula to be correct in order to get this part right. If I just said, okay, magnesium, nitrogen, so that's Mg, and probably, and let's put MgN over here, I would not be able to get the correct molar mass of MgNO3 Okay, which means my answer would not come out to be correct either. Okay, it's a real shame when everything is put together correctly, but then the only thing that's stopping you is your formula gave you the wrong molar mass. Okay, so this is why we take so much time to figure out how to put together a chemical formula. So you can read out a chemical name and say, I can figure out what that is, which means I can figure out the correct molar mass. Okay, otherwise you're going to get stuck real fast on that. Okay, so hopefully that was helpful. And again, hopefully you can see that these conversions are not really different than the other unit conversions we've done in the past. The only thing that's new is these conversion factors that are going to look a little bit weird and sometimes are a little bit more kind of intensive with how we take care of them than other conversion factors.